For lesson 2 in unit 4, we're going to focus on isosceles and equilateral triangles, a couple properties that can be useful to some of our thought processes that we'll kind of explore a little bit more in the coming days, but we're going to get some algebra out of the way, some solving of equations, find the measure of the angle, kind of classic math type stuff, geometry that you've probably done in other classes, but we're going to outline some of the geometric thinking behind some of the geometry and algebra computational work that you've done in the past. Our goal is to make sure that you will apply concepts, theorems, fun facts about isosceles and equilateral triangles, and we'll use it to do some exercise work. So nothing too fancy here. This is going to feel like probably the most math class-ish stuff that we're going to do in this unit. And you know what isosceles triangles are, you know what equilateral triangles are. Just make sure that you write down these review concepts for equilateral and for isosceles. But there is this plot twist that we want to make sure we understand about isosceles triangles and equilateral triangles. We've sort of spoken about this already back in Unit 2, that if we know things about the sides of triangles, that gives us information about the angles. And conversely, if we know information about the angles in triangles, that will tell us what sort of special triangles we are dealing with. And so this might be useful information. We will apply the triangle angle sum theorem to a lot of our work. And so just be ready to add up angle measures to equal 180. All right, so nothing too fancy again. We've kind of already done this back in Unit 2, and we're going to explore this again here in Unit 4. So again, an isosceles triangle is a triangle where the legs are the congruent sides of the triangle, where we have a base that is not necessarily congruent to the other sides, and we also have the vertex angle, which is between the congruent legs, and the base angles, which are opposite from the congruent sides. All right. Now, when I say opposite from the congruent sides, what we mean are, if these sides are congruent, then these are the base angles. They're opposite from those congruent sides. Another way to say that is that those base angles include the base. We're going to use this language of included sides between angles and included angles between sides. And so for example, in this case, this is the base, and then these angles are the angles that include the base. The base is between those angles, and so we would call these base angles in that respect. Now, base doesn't always mean bottom, so if we had our isosceles triangle drawn this way, all right, these would still be the legs, all right, and this would be the base, even though it's not on the bottom. The whole point of understanding that vocabulary is it doesn't matter which direction the triangle is oriented. If you turn your paper, it doesn't change where the base is. It doesn't change where the congruent legs are. It doesn't change where the base angles are. So be ready to investigate that while we do some of our exercises. Sometimes it's helpful to turn your paper so that the base is on the bottom, if that kind of helps you think through things like you would have approached these questions and some of these similar types of exercises in your elementary or middle school geometry classes or math classes. And so here is our first fun fact. Knowing that in an isosceles triangle, the base angles are congruent. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. The converse of this theorem is also true, and that states that if you have two angles in a triangle that are congruent to each other, then that means that the sides opposite those triangles are also going to be congruent to each other. So you may have known that already, that in an isosceles triangle, the base angles were congruent, but it also works in the other direction, that if we have congruent angles, then we know that we are also going to have a pair of congruent sides within a triangle. Right? That doesn't work if you have this angle and this triangle is congruent to that angle and that triangle, that the sides opposite will be congruent. That's not going to be the case all the time. But this will be the case within a triangle. And so a little proof, a little exploration that we can do with this is that if we have an isosceles triangle, we can reflect that triangle over its line of reflectional symmetry to show that the angle at A corresponds to and is therefore congruent to the angle at C. This rigid motion exists to reflect this part onto itself, and this part over to this other side. So A would go to C and C would go to A, and this triangle would look the same because it's symmetrical at over that line of reflection that is drawn from the vertex to the midpoint of the base. And so we have these congruent triangles. Sorry for the bell. And therefore we have these congruent corresponding parts, the angle at A and the angle at C. All right, whoops, I went too fast to that. So this is an explanation. We're not going to do too many proofs this way, applying reflectional symmetries or rotational symmetries, but it's a good way to think about how we might then make statements in our traditional geometric proofs that we're going to explore over the next several class meetings. And so you can think through this and recognize that it's true. Our proofs are actually not going to be organized in this fashion, but it is a way in which we can think through that content in those relationships. So using the isosceles triangle theorem, if we know that these triangles are isosceles, then I know that the angle here is going to be congruent to the angle there. I know that the angle here is going to be congruent to the angle there. And so this will help me create equations. Now some of those equations will just be basic statements that this angle is going to have the same measure as that angle. And so we can create that equation and find the value of x. It's kind of a weird example, actually we're going to talk about that. And then the other situation is, here I know that this one's 28. I don't know this, but I do know that this is also going to be 28 degrees. And so I would create a sum equation that we have 28 and 28, and then we also have this angle 5x plus 9, and those will sum to 180. So we'll kind of have two different approaches that we can take. And so in this case, we have 56 and 9 is going to make 55, and 5x is equal to 180. We can subtract 55, and then we can divide by 5 to solve for x. All right, and so it's kind of a strange case, but it lets us make an equation, inserting some information into the diagram that was not explicitly given, but that we know is true based on the isosceles triangle theorem. All right, this one's a little bit funny. I don't necessarily like this example just because of the way that things are drawn, but I can add 4x's to both sides, I can add 3 to both sides, and I can divide by 12 on both sides to find the measure of, I'm sorry, not the measure, but the value for the angle at x. So this isn't necessarily drawn to scale, obviously, because this angle, it would have to be 5 degrees. This angle would have to be 5 degrees, and this is obviously drawn to look more like a 20-degree angle. But it still lets us solve that equation. It does go to show that we can see that our pictures are not always to scale, and that is something to just be aware of. Making sure that we want to make sure that our answers are reasonable, but we also don't want to just trust everything that we see in the diagram. If we're given explicit information, like these are congruent, explicit information, the measure of these angles are these values and these values, this expression and that expression, then we will have to use that information, but it doesn't necessarily give us a clue to the size of the angle, the measure of the angle. We're not using a protractor to measure those, we're doing the algebra to compute what those measures are going to be. All right, over here, we have some information about side lengths. And this is using the converse of the isosceles triangle theorem, knowing that if these angles are congruent, then that means that these sides are congruent. This is irrelevant. So still draw that and label the sides, but note that this side length right here is not useful to us in this particular case. If we're going to solve for x, then we're going to make the equation that x plus 20 is equal to 8x over 3. Likewise, over here, this is an irrelevant side. This is the base, and it's not relevant to the situation because these are the sides that are congruent to each other. So I need the equation 8x minus 1 is equal to 4x plus 5. I'm not going to use the 2x plus 11. And you need to understand why. You need to understand that the sides opposite those congruent angles are congruent, and it's irrelevant what the size of the base is, all right? I can't create an equation with all three of these sides unless I know what the perimeter is. So here I can create this equation and I can solve. I can multiply both sides by 3 is usually the way that we would do that. That gives me 3x and 60 is equal to 8x's. I can subtract 3x's from both sides. I can divide by 5 on both sides. If you have questions on the Algebra 1, feel free to ask. I can subtract 4x's, I can add 1, and I can divide by 4 to find out what x is equal to. Answer that as a decimal is fine too. 1.5 is fine if you'd like to answer it in that way. So being able to create these equations and solve these equations are going to revolve around a couple things. First of all, creating your equations is the geometry part. And so if you know the geometry, if you're learning this content, then creating those equations is kind of the punchline. This right here is all of your Algebra 1. And so what you want to make sure is that you understand the new material, or what, not the new material, but what we're teaching, that you understand how to create this equation. And then if you're having trouble with the Algebra 1, at least identify that you're having trouble solving the equation, you're having trouble with Chapter 2 of Algebra 1 or whatever. And if that's the case, then we can get some additional practice with just solving equations. But what I'm going to care about initially here is, can we write the correct equations? Whoops, this clicker is kind of going fast. Theorem 2 deals with the bisector of the vertex angle and the perpendicular bisector of the base in an isosceles triangle. So here, this says that the bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the opposite side. We will actually prove this in lesson 3 and 4. The purpose of it today is we can kind of think of this like that line of reflection that we talked about in the proof of theorem 4.1, showing that these angles were congruent. Basically what we're going to find out is that these triangles, these two halves, are congruent to each other, and we can use the fact that if the triangles are congruent, by definition their corresponding parts are congruent. And so we'll talk about why these are going to be right angles in that next class in 4.3.4.4. So what we've got going on here is, if we bisect this angle, cutting it in half so that this part is congruent to that part, then that means that we've cut the opposite side in half and we've made right angles. And so that's kind of the punchline there. We can use that and apply that in this type of exercise. So draw that picture as best you can, triangle PRS, and then draw the segment SQ that bisects the angle at S. Right, the big angle at S. What we know about this isosceles triangle is that these angles are congruent to each other. All right? We also know that if I bisected this vertex angle, then that means I've made right angles at Q. So if I'm going to find the measure of angle RSQ, that's this one right here, I can do this two ways. The first way, what most of us are going to do, is they're going to take the measure of the angle at R and the measure of the angle at S and the measure of the angle at Q, and they're going to sum it to equal 180. So we're going to take 31 and the one that we're solving for, RSQ, and SQR, which we know is 90 because perpendicular segments make right angles, and right angles have a measure of 90. And we can combine our like terms. The measure of RSQ plus 121 is equal to 180, and then we can subtract 121 from both sides to make sure that we identify that this is going to be 59 degrees. All right? We don't have to put degrees on there because I know that we're using degrees. All right? The other way that you can do this is you could simply note that these two angles are complementary. If this is a right angle, then the two acute angles are complementary. We proved that in our Unit 2 test. And so we can write the equation that 31 plus the measure of angle RSQ is equal to 90, and we can just subtract 31 to find out the measure of angle RSQ. All right, finding the length of PR. Finding the length of PR is this whole thing. I know that this is 4, and I know it's congruent to this segment, and it's also 4. So the total there is going to be the length of PR is equal to the length of PQ and the length of QR, which is going to be 4 and 4, which is 8. Now, if you want to show all that work so that you can explain where that answer came from, I think it's healthier than just writing the answer, all right? Because that way it certifies that you understand the process, and so that's why I'm showing that work. I'm using segment addition to add the parts and go from there. Angle addition to add the parts to get the total, etc. All right, now when it comes to equilateral triangles, we learned in Unit 2 that equilateral triangles were also equiangular. And so we talked about that in the last unit, or 2 units ago, and we're going to use that finally here today. So the concept that an equilateral triangle is equiangular and an equiangular triangle is equilateral is very useful to us. We know that each of these sides are congruent. That means that each of the angles opposite those sides is also congruent to each other. And we determined in previous lessons, and you probably knew this even from elementary school, that the measure of each of these angles in an equilateral triangle, each of the measures is 60 degrees because they're all congruent. They all add up to 180, so 180 divided by 3 is 60. And so we know the measures of each of those angles. So in this particular situation, we can find the measures of some of these angles, maybe even all of these angles, by reading the markings. All right? There's no numbers in this picture, but we can still find the measures of these angles. So it's asking to find the measure of angle BAD, and that's if we know that the angle CBD, this whole thing, is 130 degrees. All right? So the way that we're going to explore that and understand that is, I know that this is 60, I know that this is 60, I know that this is 60. And so if this whole thing is 130, then that means that this part is 70. And so if we know the measure is the whole thing is 130, and we know that this part is 60, then we know that this piece has to be 70. These angles in this isosceles triangle are gonna be congruent to each other. So if this is what we're looking for, we'll call that x, then this is also the same measure. So looking at just this triangle, we have that x and 70 makes 180 degrees. So we can solve this equation doing basic algebra 1, chapter 2 algebra 1, to find out that x is going to be 55 degrees. All right? And we can look at this picture, and even though we aren't labeled with any numbers, we do have to be given a little bit of information that we can explore and use. We don't have parallel lines, so we don't have alternate interior angles congruent, but if we were given parallel lines, we could use alternate interior angles, and we could have a little bit of fun with all of that awesomeness. But for here, we want to be able to create our equations using our triangle angle sum, and using the fact that we know, even though they tell us that this one angle is 130, we know the measures of all of these angles, and we know that these have to be the same. And so we can find the value of that angle BAD. All right, moving on. Whoops, I'm out of the window. My bad, hold on. All right. So I would like for you to try this. It's a very similar picture, all right? But draw this one along with all the other ones. Hopefully you have all of the examples drawn, all the pictures drawn, and you've done all the work. But here you are given this information. I would love for you to try to find the measure of angle PNO. And then once you find that, you have to do this one. Once you get that, use your answer to try to find the measure of angle NOP. Go ahead and try that one. Pause the video for as long as you need. And here is our summary. For each of these things, you want to also think about the converses being true. So if you know the sides are congruent, you know the base angles are congruent, or the angles opposite them. If the angles are congruent in a triangle, then the sides opposite them are congruent. If you bisect the vertex angle in an isosceles triangle, you are bisecting the opposite side at a right angle. It's the perpendicular bisector. And conversely, if this is the perpendicular bisector, then this is the bisector in our isosceles triangle. This has to be an isosceles triangle for that to work. Over here, if we have an equilateral triangle, it's equiangular. If it's equiangular, it's also equilateral. Hopefully now you understand enough about isosceles triangles and equilateral triangles that you can find the measures of angles.